Hi everyone, this is Anand again. So I hope you are able to take a look at the first lecture set that I sent, which is essentially an hour-long summarization of the first 8 weeks of the course that we covered before the lockdown started. And from today onwards, we are going to start the rest of the lectures, which will be at a much slower pace. In the sense that it's more like a classroom lecture speed. Um, and so let me get started with the second half of the course, which is essentially the methods that are related to free energy, or um, more appropriately, free energy difference calculations in mostly biological biophysical systems, but also we will do some examples in simple physical systems. So let me just start by sharing the slides with you, which will help me go through the content, and I'll share the slides also with you guys in the class. And so the idea is to, because this is a very tutorial based course, the idea is to be able to, let's see, yeah. So the idea is to be able to do some exercises for every set of lectures that I give. And so most of the things that I teach today and going forward is actually taken from a very nice a collection of articles put together by Christopher Chipot and Andrew Pohril, and it's an amazing compilation. And those of you who are very interested in this area, I urge you to have a copy of this, or kind of go through this. The historical perspective. The first chapter deals with historical perspective of how the free energy calculation came into being, starting from all the way going way back to Lev Landau's ideas of perturbation theory, and then John Kirkwood's seminal work in essentially is the one. John Kirkwood is the one who actually can be credited with defining the term potential of mean force, and also reaction coordinate or collective variable, and some of the seminal work done by him in perturbation theory as well as thermodynamic integration, and then following him, uh, Robert Zwanzig's work, and a lot of other people who have contributed to this elegant and very important field of computationally calculating the free energy difference between different states of physical and biophysical system. And so I loved the historical perspective in the first chapter, and also like discussions about um, non-Boltzmann sampling, and what are the efforts that went in, starting all the way from um, let's say Card and Value and Ferenberg. So the idea of multi-stage histogramming, and then going to weighted histogramming, and so on and so forth. So it's a good book to go through, and very well laid out. So what I've done is, generally I've prepared my lectures um, taking things from this book, and as well as a lot of other books which I have mentioned in our course, and probably it is there in the uh, first few lectures. I have discussed those books, but then there are also a lot of other papers that I have compiled these lectures, the following lectures that you will see. And so for this, which is the one of the first real lectures on free energy calculations, there is a nice review article way back about 10 years back, actually now, by Van Gusteren. And it's pretty nice because it actually breaks down there are many, but this is one of them, which breaks down what are the things that are required for doing carrying out a free energy calculations. What are the things that are important in terms of force fields, Hamiltonians, then the sampling, and then the different ways in which 3 or 4 fundamental ways in which people think about uh, the techniques itself. Okay, so I'll try to talk about all this in the coming slides. and I don't need to sing to the choir, but I mean, I don't want to go into why free energy or calculations of free energy differences is so important, because it's one of the most important thermodynamic quantities, which tells you, which gives you uh, uh, a view of the thermodynamics of the system, where it wants to go, what are the barriers, what is the free energy difference, and what are the driving forces, and so on and so forth. So some of the examples eventually, hopefully, we'll do in the class by the end of the semester, and this week probably won't be able to do online, is take a protein, and let's say that protein has two known stable states, then see if we can transition it from one state to the another and look at the intermediate. So this is one of the examples from my lab, where we have looked at a RFAH protein using one of the methods developed in the lab, where you can see like the how the transition has taken from one conformation to the another, and so there are many others. I think one of the favorite project assignment by the students have been to take a molecule, for those who are in the membrane biophysical area, is and look at the potential of mean force of taking that small molecule from the middle of the bilayer to the solvent. And there are some of you who will be who are more interested in um, in membrane organization, or in nucleation and other things, so you can pick up things on phase transition too. So there is one big project that all of you have to submit, and I hope all of you are working on that as a part of your credit. So 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 all of you by now have seen this equation many times. The free energy, the absolute free energy, is minus 1 by beta, beta being the kb 1 by kbt. And the logarithmic of partition function, and you have done exercises in the class showing how that came about. So I won't go into the so I will be talking a lot about the partition function in the coming slides, and also like try to motivate the fact that why is free energy, or in this case absolute free energy, such a difficult thing to calculate or measure or derive. So one thing is for sure is that the partition function itself is a non-trivial, like we mentioned in the last class, a non-trivial, it cannot be represented analytically as a function of temperature, volume. It's the state variables straightforwardly. And because of that, you just can't do mathematical operations on it and hope to end up with the absolute free energy value. And which we will discuss. So we will take example of, let's say, an ideal gas, where actually the analytical function for the partition function is known, and see whether we can extract certain thermodynamic functions or thermodynamic properties out of it. But in general, Q is a really difficult to write analytically. Why is free energy so difficult to calculate, or not, so doesn't come straightforward? Can we actually, we can go back to the definition of mechanical mechanical features or functions and or properties, and entropic or thermal properties. So for example, mechanical properties are derivatives of the partition function. For example, energy, which is pretty well known, and energy, as I've taken this equation from Andrew Leach's book, and you can see the energy, which is represented as U here, is written as kBT squared by Q, del Q by del T, and all of you have actually done, all of you have taken this equation and done homework, and also taken molecular simulations of simple systems, and actually calculated the the energy of the system. And if you expand this, if you actually wrote, so if you put Q is equals to the summation of exponentials of each of the e exponential of minus beta, let's say ei, each state, and the summation goes over all the i's, then you end up with an expression for u, which is actually a product of the uh, probability distribution, which is written as rho here, and the energy E, right? So this is essentially, you can think of it as a sigma uh, E and P of E, or the probability of E. So that's what we have in PI, EI in a bracket, right? And so this comes easily, because what happens is that when you look at the products, so you can think of it as a summation of products of probabilities and the values of the energies for that the probability for energy and the value of the energy. And so what happens is, because so we know that and molecular simulations will sample lower energies, and in this particular case the sampling is good enough, and you would get a decent uh, because the lower energies are more populated, so the rows are the weights on the energies with the lower energies are higher, and so you end up getting a nice energy values. But what happens in the free energy is, which is written as A for Hampson free energy here, is that if you expanded the same term minus kT of ln q and wrote it in terms of the sigma, which by expressing q as a summation of uh, the Boltzmann probability distributions of energy, you would end up with which you will see in the coming slides how you end up with this. You would end up with a product where that is the probability distribution function and an exponential of the energy term. Now, because of this, what happens is that the higher energy terms, because there's an exponential associated with it, the contributions to the overall summation of higher energy term is significant, even though you may have a lower probability distribution or lower weights on them, right? And so even though you have a lower weights on the higher energies, but because it's a product of the exponential of the energies, it ends up having a significant contribution, and that is why you need to sample the higher energy states of the system as well, which is non-trivial, because the energy landscape or the minimization or standard molecular or Monte Carlo simulations tend to take you to the uh, to the to the lower state of the um, energies, right? And so this is one reason why. So this is an important concept which you guys should understand about the thermal parameters and the mechanical. So for example, it would be extremely difficult to calculate Q, which is itself a thermal parameter. Entropy, or let's say chemical potentials, where it's not a derivative. You cannot, but properties like energies and others are quite straightforward to get, which we do it all the time. So this is because in short, free energy calculation, one thing is difficult because generally the MC or MD algorithms tend to sample lower energies, and as long as the weights of the lower energies are dominant, because there are more, just going by the P is equals P is proportional to the exponential of energy by KT minus energy of KT. Those probability weights are higher, and so the contribution of the higher energies to the average is much low, and so you get away for things like energy. But when you are calculating free energy, or in this case absolute free energy, the product the uh, the weights of the energies, higher energies, are small, still the same, but because now the product is with the exponential of the energy, it's a large number, and so the product of them becomes significant uh, for the average value of the A, and that is one reason why you need to explore, or you need to sample those energies, and you just can't uh, get away with it. So that is one reason why sampling the whole space faithfully becomes critical for calculations of. And of course, the other reason is that it's not so straightforward to just get energy values of a system that is in thermal equilibrium with so many. The sampling itself is a very challenging problem, which we'll discuss in the coming slides. Right? Okay. So partition function. I've gone through the partition function Uh, I've gone through the partition function in the last class and few times in the past, so I'll quickly rush to this. The whole idea is that, which we already discussed in the last slide, is partition function simply written is a summation of, for a canonical system, is a summation of um, the exponentials of the Boltzmann probability distribution that we know about, right? Exponential of minus beta EI, where you can think of EI as a state of the energy of the state I. And so there are n number of, in this case, a discrete system, n number of energy states, and it's a summation of all of them. So so it's actually, um, like I said before, non-trivial to formulate Q analytically because of various reasons. And the moment I give you an example of an ideal gas, you'll see like why it becomes so difficult. And this is a famous equation that all of us live by, and is the probability is proportional to the um, so this is a Boltzmann weights that that's come about for the probability of a given state. So if you know the energy of a state and you know the partition function, then you can know the probability of the state. Easier said than done. And we talk about that. We discussed why Q is a measure of the accessible state of the system. So we'll see how that. I'll just reiterate the point once more about the accessibility of the accessible states of the system, because there are methods in the future where we will change the by changing the temperature or by changing the Hamiltonian, we'll fiddle around with the accessible states of the system. So we'll try to access more and more states, right? Because that's the whole idea of sampling each state if possible. And so again, it's going back to the same old discussion. So I'll just focus on the right hand side of this slide on this thing that I've written. So first of all, I would like to excuse myself, or you'll have to excuse me for like doing a job where I have written the equations on the paper and then scanned it and or taken a picture of it and posted it as a slide, in order to keep up with the speed of the course. So and since you don't have access to scanners, or you're just stuck at home and don't have time to write all these equations. So here, okay, so I would like you to focus. So we know that the Q is proportional to temperature and energies and also volume in case of um, in the canonical ensemble. And so you can write it as a native, so the ground state plus the excited state or non-native state, which we have written here. And this I have written because I wanted to show you guys something. So when you write the density of, so then you're trying to look at the density of states of the system. And so there are two things that matter here, right? The temperature at which you're operating and the density of the, so how close are the energy states, right? So suppose you have an energy landscape that moves, like has a very small valleys versus energy landscape that is having deep valleys, like one valley here, another valley here. And so you have a larger gap in the energy state. So it's like um, a system A here where the energy, the density of the states are very, very close to each other. And then there's a system B where the density, the states are far apart from each other. And so you can think of many systems where you will have um, each situation. And so we'll discuss like what happens here. So let's see. So the left-hand side is, so the equation remains the same all the time, right? And so here, if you take temperature 0, right? So the second term here, the 1 by kT becomes infinity, right? And so this becomes e to the power minus infinity and goes to 0, right? Because it's 1 by infinity and all the terms of the summation become 0. And so you end up with Q is equals to 0. So what does this tell? At temperature T is equals to 0 or tending towards 0, the accessible states of the system is 1. You just have the ground state, right? And so imagine you doing, which you will become very clear in the, when I start teaching you a couple of weeks from now, replica exchange methods, that so for there are systems for which you need to increase the temperature to access more states. Okay, and as you increase the temperatures, you are able to access more and more states of the system in general. Okay, so for example, at t is equals to infinity, which is theoretical number here, but in our case, it will be like a high temperature. Generally, we will be doing biomolecular simulations around the physiological temperature of 310, or some people do it at 303 or 300 Kelvin. But when we're trying to explore states using temperatures, we will go all the way to 600, 700 sometimes. Now, it's another matter how um, how the temperature plays out in terms of physically how relevant this is, but in terms of just from a theoretical perspective, you're trying to explore as many states as possible. And so what happens with a very large temperature, then look at what happens here. This one, so this beta becomes is nothing but 1 by kt, right? So the t becomes 0 because it's 1 by infinity. So that's a 0 term here. And so each of the non-native state is contributing 1 to the summation, right? So you have 1 plus the number of non-native state, and that basically, so you are now, so you have all the states that are accessible to the system. So the system is able to access uh, all the states at t is equals to infinity. So this is one. And this is something that gets played out or becomes very evident when we are doing a replica exchange method, or when we are trying to perturb the system by modulating the temperature of the system to access different states. The other aspect that is also very important and interesting is the density of the states. So there are, and so this is again, so I'll always try to relate it to how these concepts are connected to the methods that um, we are going to study. So let's first just go through this the things that I've written on the right hand side of my scribbles. So the figure on the right may do an explanation of this job. So let's say that you have this bottom line as a ground state, and we'll take the B, okay? And let's say that another state is at a slightly higher energy, and so you can rewrite the Q as a difference. So you can always rewrite the Q. So you can write, you can assume, because it's a reference that you have chosen, E naught as 0, right? Because it's an energy term. So you are free to choose where you want your reference to be, and we say that the ground state is 0, or you can just call it E0, right? So then you can write the Q as, so that you can write the, and let's say you write the Q as this term, which is completely fine to do, except that there are total n minus 1 non-native state here. So there I have written n, but you can think of n minus 1 non-native state and 1 native state or ground state. And so if you take this as an out of the equation, and then you can like as a out of the bracket, then you can write the whole thing as a difference. So 1 plus the difference between exponential of the difference between the energies with the ground state. So note that all the other states are now written as e to the power minus beta ei minus e0, right? That's what it is. So now let's see what happens here. So this can be easily written. And so see, so now imagine that the ei, and so imagine that the E1 is very close. Okay, we'll take two different cases. So let's imagine that the first state after the ground state is at a very high, the energy difference is, or the first non-native state, it has a very, the energy difference with the ground state is very, very high. For example, let's say that first state is, ground state is here and the other state is here. So ei minus e0, or ei minus, yeah, e1 minus e0 becomes a large number, right? A large positive number, and imagine, for the sake of argument, that it becomes as large as infinity. So this term becomes e to the power minus infinity, right? Minus beta is a small number into infinity, and so this becomes 0, right? And so you have all the other terms will also become zero, because if E1 minus E0 is a large number, then E2, which is even higher than E1, minus E2 will be again a very large number, a number larger than E1 minus E0, and they will also give you zero. So what happens is that if the energy states are separated by a large number, even the first ground state and the first state is excited state is far away from each other on the energy scale, you don't sample much. You just sample the native state, right, which is Q is equals to 1. So the accessible state of the system is 1. And this is a major problem, right? You have a protein in a well here, and then the next conformation is at a much higher energy states. And so the question becomes, how do you go from here to there? And so so that is a major thing that, and let's say you know that there is another state, or you would like to explore at least all the other states that are possible by that protein, or any system that you're interested in. It could be the movement of the, let's say, a butane molecule, or I mean, whatever, small molecules, or whatever you want. So, uh, so, so let's take the other extreme example, right? So we say that each of the energy states are almost equal to each other. So, or rather, you have the ground state, and the first excited state has, let's say, an energy difference that is maybe thermal noise, or a little bit above thermal noise. So you can say that the delta E is almost close to zero. A thermal noise would be, let's say, 0.593 kilocal, but let's approximate that as we have been doing, like, because in order to accentuate the point, sort of making large number as infinity and small numbers as zero. So in that case, what happens, you have the first excited state, and the difference between the first excited state and the ground state is zero. So this, and so in that case, what happens, that the Qs actually end up um, being all the, so you are able to access all the states, right? And because they can jump, because there's such small energy barriers, that you should be able to jump from one state to another without much ado. And so this is something that we actually do in the simulations. You'll see in the coming. So if you have two states, and today itself we will do this. If you have, if there's this exercise that is based on the free energy perturbation theory that I will cover today. We will see, like, if you want to go from one state, if you want to sample from one state to the other state, how do you build up these intermediate states in between by creating all these intermediate constraint systems that bridges the gap between the energy states, and so you're able to go from this state to that state via all these small steps. That this is not just a theoretical academic pursuit, but it has strong relevance. Both these aspects of temperature and the density of, like, trying to bridge the gap between the two different states through intermediates, fictitious intermediates that, or rather forced intermediates that you do, but very important from that point of view. Okay, let's see, what do we have next. Okay, so already done this. So measure of accessible state, I've discussed a lot about it, and this is what I was saying. Like, you have E, average energy, as sigma of Pi EI, right? And what happens is that, because the smaller the EIs where the molecular simulations tend to take you, is the energy minima, right? And so you have more sampling of that. But the fact is that those are higher populations, and so the higher energy states are very rare in their occurrences, and so you end up having a more or less faithful representation of energy, even though you may fail to sample the low probability states. But as soon as you come to free energy, that's not the case, because the whole thing is rho I, or Pi, into exponential of EI by KT. And so in that case, the higher energy terms have a significant contribution in terms of their value. And even though their populations are low, they contribute significantly to the whole summation or the average. Okay. Okay. So we all wish that we could find or write analytical expression for the partition function. And like we have discussed in the class before, once you have a functional form for the partition function, I mean, things just fall in place. You just derive, integrate, second derivatives. You do all kinds of things and end up getting so many different things like pressure, volume, entropy. I mean, we did, for example, in the class, we did CV, specific heats, and a few other things, right? So that is something that as a exercise we should be doing. And for that, what I've done, given two examples for this class. Okay, one is from an ideal gas, very straight. So you open up any book on statistical mechanics or statistical thermodynamics, and you end up uh, looking at the partition function of a single particle, non-interacting, and so on and so forth. And then you can write the partition function of the whole system, ideal gas, and then from there you can derive some of the equation of states and a few other things. So we will be briefly going through this, and as an exercise, I would like you to try out harmonic oscillator example. Okay. So let's move on. Feel free to shoot me emails. Also call me if you have to, if some things are bothering you a lot with respect to conceptual understanding and slash or about your projects or assignments or tutorials that I have been giving you. So you all have my number and my email ID. And once we have the 101 sessions, the weekly, hopefully through Zoom or some other ways, a session, then I'm ready to answer all the questions that I'm looking forward to that session actually. So I'm not going into the, okay. So the ideal gas partition function, just a minute please. Yeah. The ideal gas partition function is written as the partition function of a single particle to the power n, okay, divided by n factorial. And I'm not going into how that small q came into being. That's itself is another lecture altogether. I urge you to go and look at the StatMech or Stat Thermo books and look at how it is derived. So this is not the in the scope of the things that we are teaching. I'll just give you the partition function of a particle of an ideal gas partner. But let's see why ideal gas you could write it uh, when you know the let's say you know the uh, partition function of a particle, and this is because they're non-interacting, right? So because they're non-interacting, you could just take a product of them. It's like, you know, probabilities, joint probabilities. When you know that if those two probabilities are independent of each other, then you can take the product of those two probabilities. Otherwise, you have to think about the writing the joint probability in a way where uh, the, uh, the, the two different probabilities has a way of showing an overlap. So because they're non-interacting, you could just take products of it. They're identical. So you can just write as Q, 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 Q. So all of them are Q, right? And they're indistinguishable. That's why you have a n factorial here. So imagine how many systems are non-interacting. I mean, very, very few, correct? In real world system. And of course, they're not identical in the sense that they are in different environments and so on and so forth. It's indistinguishable is not a big thing here, because the harmonic oscillator that you will take or some other examples that we'll take will not have that. But this is one of the most simplest, or rather the simplest. Uh, there are other simpler systems that could have been used for like disseminating the idea of writing partition function in analytical form, like two-state systems and other things. But we choose this because some things jump out very nicely out of it. So systems are actually very interacting. They are not like non-interacting. I mean, simple ideal gas move away from to a, let's say, a real gas itself. There is a lot of interactions going on between the particles, and they're not just collisions that with no interaction term. It's, I mean, to run a molecular simulation with no interaction, a realistic molecular simulation is kind of very non-physical. and so it's really difficult to write Q, correct? And so let's see if once you have the partition function written up, then what all you can do. So of course you can take a logarithmic of capital Q, and you end up as as the term that I show here, and that can be written as this one, right? And so you can write the free energy as minus kT of ln Q, which will be a big expression. But let's see what all things that you can get out of it. So if you take a derivative of F with a free energy with respect to volume, um, you can do this exercise. So all other terms will cancel except the terms that carry volume term with it, right? Because this is a system with NBT, so temperature, volume, and 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 the numbers, and so you will end up with del V by del F by del V is equals to N by V, right? And into kT. And so we know that from the definition of pressure, pressure is a conjugate of the volume in the free energy framework. And so you know, like the left hand side is the pressure. And so right away the pressure equation jumps at you, right? So straightforward. I mean, you know the partition function and you know the pressure of the system. So wish we could know the partition function of all the things that we are dealing with, and we could just write the whole phase space of the system. That would be awesome. You can write the average energy of the system, which is also very straightforward. You can write the specific heat, which is nothing but, which also you can, and then entropy and other terms can be written. So either you can write entropy as a, from the equation minus del F by del T at V, constant V, or you could, because you have calculated U and you have calculated F, which is this, then you can also get the entropy from just doing an algebra on S is equals to U minus F by T kind of thing, right? And so you will get a entropy of, so do that exercise at your home. Okay, look at what is the entropy of the, what is the entropy equation for a ideal gas? Does it make sense to you? And look at the other like the equations that you deal with it with the Gibbs equations. And the other thing that I want you guys to try is the harmonic oscillators. Okay, a little bit more complex than the ideal gas, but something that I think as an exercise you can do to get more clarity on both how to think about partition functions, and also like because it will help you keep you in good stead when you are actually doing real systems. And so there are other systems that you can look at. You can take a two-state system, I think very elegant system for understanding these concepts, and go. So just pick up some book and can go through all that, and do ask me if you actually want those equations and want to do the algebra yourself. Okay, so at home try this one. Okay, so I'm just taking a simple harmonic oscillator. It's non-interacting, which means that you can take products of each of the oscillators, um, and so you can write the Hamiltonian of the system as a classical Hamiltonian of oscillator, which is the kinetic energy term and the potential energy terms, right? And then you can so you can write your partition function in the classical way. So you assume that the momenta is from minus p to plus, minus infinity to plus infinity. I mean, your oscillators can have infinite positive and negative velocities of momentum and infinite extensions and compression, which is, we know, is doesn't happen, but that's what you write, right? And so you end up with a Q. So you can show that the Q is equals to kBp by Planck's constant omega. Remember the error function integration that we did in the class, right? Where we took e power minus x squared and integrated it, and then we had to, so that is I, then you do a I squared, and then you do take it in the radial coordinate system, and you could do this. Or you can simply use e to the minus x squared integration using the error function that is available in these integration tables. And you should be able to show that Q is equals to KBT by this term. Okay, and omega is nothing but rewriting the harmonic, the potential energy terms in terms of the frequency of the force constants spring that you have. And because the non-interacting particle, you can write Q is equals to the product of all of them. And once you have that, look at what you get for average energy and whether you can and whether you can prove the equipartition theorem. Okay, and so that would be a good exercise to do. Now in the systems that, okay, so I hope all of you will pick up your pen and paper and kind of try to do this exercise and then look at how the the kinetic energy term, the potential energy averages, how do they come about? Okay, and also look at the average energy of the system and whatever else you could get out of your of the partition function, because we have often said in the class that once you have the partition function analytical expression, you can know everything about the thermodynamics. So why not try it out, right? And see where all you can take it. Now, so these two systems that I have talked in the class, and the third system that is very common to use for a expression of an partition function that can be expressed analytically is the two-state function, which I have not discussed. But those of you who are interested in phase separation or like two-state protein models and so on and so forth should also pick that up and try to do some algebra with it. Okay. Now let's see. So in fact, I remember in one of my assignments, I may have given homework for the two-state system. If I have not, then maybe I'll give you an assignment where you can actually write the whole, so go through the whole exercise. Okay, so far we have talked about absolute free energies, but absolute free energies, like we know, because of the limitations on writing the partition function analytically, sampling issues, interacting particles, so many different types of them and so on and so forth, it's not straightforward to, not just calling straightforward is an understatement. It's one of the most difficult things to do, right? And so we end up doing a relative free energy calculations most of the time, and that's pretty useful. I mean, if you can get the information that you want from relative free energy, then the job is done. So as long as you can calculate the free energy difference between the different states that you are concerned about, you would know like which is more spontaneous, what are the aspects about it, and another thing. And the free energy difference could be simply written as -1 by beta ln of QB by QA. And so because you just take a logarithmic and the difference of the two logarithmics gives you the log of the ratios of the two partition function. So and you may not connect it to right now, but we have done such a thing in the class. So where we have taken the probabilities, we have taken I've given you the energies like this thing that I'm showing you here, right? So there's some examples that I have made you guys do in the previous assignments or tutorial assignments, essentially, not tutorials, where remember the example of people living in first floor, more populated, and then as they go along the floor of 100 tower build, 100 floor tower, then how so I there was a penalty to each floor, and so we are looking at the energy penalty for that and trying to find the distribution. Or let's say a more relevant example for our biomolecular simulations would be that you have these different protein conformations. This is an image taken from Kendall's book on driving forces. The driving forces book, I don't remember the exact name of the book, but something to do with the driving forces of physical system or molecular driving forces. An awesome book to have with you. So this is an image taken from that Professor Kendall's book, and so from one of the exercises or the or the chapters. And so you have these 6 different conformations of the protein, and let's say that they exist in these 6 conformations only. Okay, that's an assumption we make. And so you are able to calculate the average energy of these different states. Then can you tell what would be the, so if you said that there are 100 of this, or let's say a million of this this protein in a jar of water, then could you tell like what percentage of it would be at, let's say, state A versus state B versus state C and so on? And that you can do, right? We did that exercise. We said that if you wanted to know what percentage of protein exists as A, you would end up calculating the exponential. So you basically find the whole partition function by summing over e to the minus beta ei going from A to F, and that gives you the numerator, and then you at the denominator you have that state e to the minus beta, and that gives you the fraction of the system, because we are making an assumption that there are just the 6 states, right? And so we were able to give relative populations, and if as soon as you are able to give the relative population, you can actually connect it uh, to the probabilities. And the assumption here is that the sampling is really well done. So let's see. So so the question is, we did this part, right? We took this part, but what, and then we said that the free energy difference between them is could be written in terms of what we are saying here, and we are not connecting the 2 parts, right? So that is a connection that is important to make, because probabilities, maybe it's easy to count things in a simulation, assuming that the sampling is really nice one of different states. Suppose you had like eye of a god, or eye of like the best microscope, or things that you could see, and so you could see you could track the protein, take a single protein and track it, like how it is moving from one state to the another, and you can count it, right? And so once you count it, you can get the probabilities of it. Or suppose there is another way in which you can measure the energies of the system, and are able to distribute that into weights of different energy contributions. So those are the things that are non-trivial. But what we have to do is to connect the probability, this term, where we are saying that if you know the probability distributions, probabilities, then they are equivalent to the ratio of the partition function, which is something that we should be thinking about, right? And so once you have the ratios of the probabilities, you end up reporting something about the average difference in the free energy. And so let's try to do that right now. Okay, I don't think, let me see the time. It has been, let me see how much I can cover today. I don't want to go. Okay, there's lots to cover. So what I'll do is I'll break this course into 2 parts. I was hoping to finish everything today, but it may be over an hour to finish this. So let's try to connect these 2 things first. So I take an example here, okay? So imagine that you have our favorite example when it comes to conformation. Let's say a 4 carbon, or a molecule that is, let's say a butane molecule represented as 4 beads. And it can exist in this form, and it can exist in the other form. And so let's say these are the 2 different states of the molecule. And there is a, so how do you, so there is something that we have discussed in the past about collective variable or reaction coordinate. So you define the overall system by like have a integrated out representation of the system, and that representation or that variable is able to differentiate between the 2 states. So we can call that as a collective variable or a reaction coordinate. In this particular case, as you can see, if you take let's say the length of the bonds, right? The length of the bond between A and B do not change. The overall length is the same. So it doesn't distinguish between the 2 states. Or even if you can say like the angle between the 2 bonds, that also doesn't end. In both cases, it's 90 degrees. So so it's one of the most challenging things for a simple system like this. It intuitively comes to you, but more complex systems, it is very difficult to actually define a collective variable that can distinguish between the different states of the system. In this particular case, we can take let's say dihedral angle or the rotation angle. So you can clearly see in one case it's 0, in another case it is 180 degrees. So, so imagine that this is the state lambda, right? So you have lambda A and lambda B. These are the two different states. And like what I said, you have a microscope or you have some ways of tracking it. Let's say you have a computational microscope, which is molecular dynamics simulation. So you track lambda, right, over time. And so you see like, okay, this is at this lambda A, and then you see that it switches to lambda B for some time, then it again goes to other states, and just keep going back. So this is a good sampling. Like this guy is able to move between A state and B state, right? And so this is under the assumption that there's a nice sampling going on between state A and state B, where you can see things moving from state A to state B, enough sampling on state B, then again jumping back and forth many times. There are um, many experiments that are actually done this with, which we should be talking about in the coming days, like forced-induced conformation changes, AFM-based experiments, even Fred-based experiments. So Fred can track these kind of things. So, but for right now, for the theoretical part of the lecture, just assume the basic assumption here is that uh, that lambda is able to define the two different states in a very clear way. There's no ambiguity about it. And also the very important assumption or things that you just take for granted is that it is able to sample nicely. Like you are, whatever should be the sampling populations for A and B over a period of time, you are able to get that going, right? Once you have that, then you can write the ratio. So at the end of your tracking, you can write the ratio between the probabilities of states that are existing in lambda B and state that is existing in lambda A by simply writing the ratio. And because this is one system which has sampled well, the partition function is same, right? There's just one Q. So you have P lambda B is equals to exponential of minus whatever. And so you can take the ratios, but you can also do a, you can write it in a formal way by writing the product of it, of the partition function. So you write the partition function, that's just that it is sampling the lambda B state only. So, and whenever it runs into lambda B, you raise a flag 1, and so you sample it. Whenever it is not, you have a 0. So this term actually gives you the sampling at lambda B, and this term gives you the sampling at lambda A, right? And this is actually equivalent to the ratio between the QB and QA. So this is the partition function that is being that represents the state B and the ratio. So this is where you connect the thing that we discussed in the last slide, where you know the ratios of the probabilities and then how it is connected to the ratio of partition functions for those states, right? And so that brings us to the that brings us to the formally connecting the probability ratios of the probabilities of the states or the collective variables of that state with the partition function that or you can call it like the partition the component of the partition function that comes about because of it lying in that state, right? So this is where the connection is made, right? And remember the assumptions that we made. Remember the assumptions that we made. The assumption is that the sample is very, very well sampled, right? That's a basic assumption. Things fall apart if you don't have that. Okay? What example can I give you guys for this? So imagine that you did this exercise in the class, right? You took alanine dipeptide and ran it for, let's say, so I think we did this exercise where you took alanine dipeptide, ran it for 1 nanosecond, and then ran it for 10 nanoseconds in water, right? And then plotted the Ramachandran map. And then you saw like how poor the Ramachandran map looked as compared to the well-known alanine dipeptide Ramachandran sampling that goes about at 1 nanosecond. And this is because it has not sampled all the phi's in size. It's still, the time is still not enough. But when you did it for 5 nanoseconds, you started seeing better. And by 10 nanoseconds, it was all like, it was actually able to reproduce the map that we are so familiar with. But this is because the phi's and because the torsional angle movements have barriers that are sort of thermal level barriers, so they can cross them. But that may not be the case all the time, right? You may not be able to run a molecular simulation and sample everything. I mean, imagine a large protein. You start with a known to have two different conformations established through, let's say, NMR or through other ways, and you take it in one conformation. No matter how long you run, it just stays in that conformation, and so you are stuck at lambda A. It doesn't go to lambda B, and so you cannot use this. You cannot just use these. Formulation there because you have not sampled well. Because the lambda b is almost zero here and not realistic, and it has to cross a large barrier and so on and so forth. So those are the things that matter in the free energy calculation business. And so let's see what I mean by that. So there are two things that become important here, right? One is ability to sample. So of course, the ability to sample well lies at the heart of all the free energy difference calculations that we do. If your MD simulation can sample a system well, for example, alanine dipeptide, I don't see any reason why you should be doing free energy calculations, because the free energy just comes about by tracking the different states. You have the right numbers for it over a period of time, and then you just take the ratios of that, and this gives you the free energy of these two different states or multiple states that or the whatever you define as states. But there are challenges that comes about, right? And we know that we connect so the probabilities are connected to the average energies. Remember this term that so we are given the energy of a protein, correct? Once we know the energy, we know and suppose you know two of them, you know the energies, then you can find the 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 probabilities, the ratios between them, right? Because you take it exponential of the energy term minus energy by kT term and you get it. So the two different things that matter is how well it is sampled, and that's non-trivial because for complex systems, it may always remain as lambda A, like what we said, a protein in one well, going from a large protein in one well, going from one well to the another well, or let's say a glass which you are trying to or a system where you're trying to look at phase separation, but the phase separation, you know it happens, but you can't see it happening because the barriers are so high. There are so many cooperative movements and so many issues with it. So it's not always trivial. So once you start a simulation, you may just end up in that state. Yeah. And we start with another, so same protein that we're talking about. If you start in another valley of the free energy landscape, then you are just in that valley. So it's very difficult sometimes, most of the times, to switch between one state to another because the barrier is so high, right? The free energy barrier is so high. So you don't get to sample accurately for the system. That thing comes about by the energy barrier itself between the states. But what is also very important and which gets left out by students most of the time is the sampling at the same state itself. Okay. So for example, in the protein example of the candle that I showed you, there are six different proteins, right? Conformations, and there is an energy value that has been given to it. But the energy calculation is something that has to be thought about carefully. For example, let's say there are six different these six different conformations. In fact, the same conformations of the proteins. You have uh, a structure that is like our favorite example of a butane, let's say, represented as four parts, four sides. So it has zero rotation angle or zero dihedral angle, right? All of them are at zero dihedral angle. But you may end up, but the thing to note is that when you're trying to find the average energy of this conformation, it's not just the energy that comes about by the bonded interactions so you can keep it fixed like this and get the bonded interaction energy, but think of all the water molecules that are around it, right? In this particular example. So you may have one arrangement of water molecules, let's say in this, where all the water molecules, the hydrogens are facing this. You can have another arrangement of water molecules where all the oxygens are facing it, maybe transiently, but yes, why not? And they will have certain probabilities. So each of these conformation, the conformation that goes beyond the configuration of the molecule in question, has an energy contribution, and that has to be sampled well. right? It's not just that theta phi is equals to 0, and once you see phi is equals to 0, that you have to wait at phi is equals to 0 and long enough to sample all the possible conformations of the water molecules around it, because the energy contribution of this conformation is different than the energy conformation of this uh, contribution, and also the population. This may be a more transient state, this may be a less transient state, and so the longer you wait and calculate the energy of the system, the better energy estimate you get of the system. This is something that gets lost many times, because I've seen people doing steered MD simulations where they just move it from one to the other, and then they say, oh, I have sampled all the different states of the, let's say you're doing a sodium chloride, which we will be doing. You take a sodium chloride at a distance like this apart, let's say 2 angstrom apart, and you want to find out what is the potential or mean force of taking sodium chloride from 2 angstrom to 9 angstrom or 10 angstroms, right? This is the exact exercise we do, and you want to get the potential of mean force. Now, you can just take and drag it like this very fast, and you would have sampled all the different different distances of the sodium and chloride, right? But then you have not sampled all the water molecules that can arrange themselves in different ways. That's where the entropic aspect comes into play. So this is something that is very, very important, and I will go into greater details about it. And this is where the connection between the entropy and average energy comes into play. Okay, so the question becomes like, are you able to take into account all the entropic contributions, and that can be coming out because the way other things are arranging around it, for a given collective variable that you are focused on, right? And of course, you cannot just calculate entropy like that. The way to do it is through the average energy. So there is a connection between the energy that you calculate and the free energy, and that is a very profound connection, right? So, okay, looks like I'll close it in another slide, and then that connection will do it next time. And so this is an exercise that we'll do, I think, a week from now or 2 weeks from now, where I'll make you guys do an umbrella sampling simulation where in fact, I will give you all the trajectories. You will just have to do the analysis. You take sodium and chloride, I'll give you multiple trajectories of sodium and chloride at different distances, and then you calculate the potential of mean force. And what we'll see is how much the fluctuations or changes in the free energy profile happens with you staying at a given distance for longer versus shorter period of time. Because even though the sodium chloride, it has a distance d apart, the contribution of energy, the overall energy of the system is coming from many other factors, like how the water molecules are arranging, what is the long range effects of not just the first solvation, but other solvations, and so on and so forth. So this is something that should be taken into account in a very, very clear way by all of you when you are doing free energy calculations, is the sampling aspects. It's not just about the barriers, it's also about sampling when you are in a given valley very, very properly. Because when you're in a given umbrella or a given valley or a given state, it's not just the molecule of interest that you're tracking, but everything around it. So there's an entropic aspect or the collective variable, but everything that contributes to the energy with that reaction coordinate that you have in mind. Okay, so the article that I started out with by Van Gustrens, Basic Ingredients in Molecular Free Energy Calculation, is something worth reading, and I would urge you guys to go and take a look at it. And there are lots of, this is 10 years back, there are lots of beautiful articles in the fundamentals, or just just a review level, broad level, philosophical level free energy calculations are there by a lot of groups, like people from Paranilo's group, Bushi and others have written wonderful articles on free energy calculation. I can just name on and on. There are so many beautiful review papers by different people, which I think you should just pick up and try to read up. There's a very nice paper in Entropy Journal, which I like. I don't remember the name of that paper. Maybe next class I can bring it up. So what is important is a model Hamiltonian. So you should have a good Hamiltonian. Imagine, so the thing that comes out of that basic ingredient article is that there are three things that you should be worried about. Okay. One is, of course, the force fields that you're working in. Imagine that uh, you have a simple harmonic oscillator, and the force fields are all messed. Like the force constant is not right. So you do a bad job of doing the calculations that you do, and that is also true for uh, the phase space that you sample, right? And so that is important, but that is not important from the point of view that what we are doing. We will assume that the force field that we are doing is the best and the best and the best force field that is available. Because force field development itself there are certain biomolecules for which force fields has matured. For example, let's say proteins and lipid to a large extent. Now there's a lot of development in IDP. There is a lot of force field development from polarizable force field point of view. So still that's a evolving issue and very difficult area to be in. But then there are, but in these cases, proteins to a large extent, lipids, the force fields have matured quite a lot. Even nucleotides, the amber force fields are rather quite good. But then there are carbohydrates, glycans. The force fields are still not mature. There are other things, other like post-translation modification force field. There are many areas where force fields are, but what we will assume is that the force field we are using is a reliable force field. And anyways, this is not an exercise in running uh, arcane biomolecules, but simple systems to understand free energy concepts. So from that point of view, I think we'll just pick out systems that are simple and have a reliable force field and not worry about the force field aspect. The second part is that comes out is the sampling, which I try to go into more details in the coming days. Like how do you sample well, right? So what do you do to the system to have as many states sampled as possible? And so that is an exercise that is easier actually than the third one, which is you can force a system to be in different states, but to know the right probabilities at the canonical, at the so uh, so systems can be at different states by forcing them to, by putting an Hamiltonian, by changing the temperature. But at the end of it, you want the population density at the temperature that you are looking for or at the environment that you wanted. So the unbiasing part of it is also quite non-trivial. Okay. And so we will discuss about all this in the coming days. So the first thing that I'm going to do, and so don't worry about it if you don't get it right now, but the first thing that we will do is the next lecture. I didn't realize that I would talk for an hour and not finish this part. But for the next lecture, what we are going to do is to be able to connect. So remember this example that I was taking, right? This example on the right. Like how do you how do you connect the energies with the free energy? And for to do that, I will actually take refuge in the elegant work by Bob Zwanzig's exponential averaging of free energy perturbation theory, and um, try to give an idea of this concept from that framework, and very elegant framework. And hopefully we will be able to do some exercise following that. So let me just, I will share this slide with you as soon as I finished with this. But the idea is that at the end of all these discussions, we should be able to actually calculate the free energy of taking an ion, an uncharged ion in water, and charging it up to like uh, 1 e charge. Okay, and then are we able to calculate the free energy difference for that? So the and what we'll do is I'll give you guys trajectories where we have ion in sodium ion in water, totally uncharged sodium ion. There's an ion with a certain excluded volume and totally uncharged, and going all the way to the fully charged. And then we are asking the question, can we find the free energy difference between the two states? And it will tell us like how much energy does it take um, for a particle of the size sodium to get charged into water, okay, or vice versa. Okay. And that's very, very interesting, and it will give you a nice perspective both about the solvation um, and also about the free energy perturbation and to some extent thermodynamic integration as well. Okay, so in the next class we will try to I'll try to cover free energy perturbation and hopefully discuss a bit about the example that Kirtika, Krishnakant and I are planning to give it to you as a free energy perturbation exercise. So I was thinking that we can split the that calculation of the delta G or delta F for charging of an ion in water, charging of an uncharged particle to a 1 each charge in water. Half of the class can do thermodynamic integration and the other half could do free energy perturbation. But we'll take a call as I teach these two concepts in the coming days. Okay, so that's it for today. And in the next class, we will try to understand the profound equation, uh, this equation where the free energy is connected to the ensemble of the um, difference in the energy, okay, by Boltzmann's, and one of the most beautiful equations in the static field. All right, so we'll come to this in the next class. And so let me pause this talk. And so see you guys uh, for the discussion that ensues on Zoom. Hopefully people from remote areas in India, like I know there are people in villages and may not have internet. Hopefully through your phone or something, you will be able to, smartphone, you may be able to come on the Zoom app. So I'll send the invite through WhatsApp. So you can simply click on it, and if you have internet connectivity through these service providers, you can just come in and I should be able to see you and you can ask questions. Okay. All right. So we will take this up going forward next. Okay. Thanks.